Okay, here's the thing. Number 10, the Mpemba effect. You've been taught the rules since childhood. Hot things cool down, cold things stay cold. Simple, obvious, done. So explain this. You take 2 cups of water. One is hot, one is cold. You put them both in a freezer at the exact same time, and the hot one freezes first. That's not a trick. That's not a misread. That's a documented, repeatable result, and physicists still can't fully agree on why it happens. It's called the Mpemba effect, named after a Tanzanian student in 1963 who noticed his hot ice cream mix froze faster than the cold version. His teacher told him he was wrong. He wasn't. When he brought it to physicist Dennis Osborne, they tested it. It was real. And here's where it gets uncomfortable. We've had centuries of thermodynamics, equations that predict heat flow with extraordinary precision. And yet, this basic kitchen observation still doesn't have a clean explanation. Some researchers say it's evaporation, some say dissolved gases, some point to hydrogen bond restructuring in water molecules. A 2020 study suggested it might not even be reproducible consistently, which almost makes it worse, because now we're not just missing the answer, we're not even sure of the question. A glass of hot water is apparently one of the most confusing objects in physics, and if something this simple is still unsolved, what does that say about everything else? Number 9. Quantum tunneling. Imagine throwing a ball at a wall. It hits the wall, it bounces back. Every time, without exception. That's not a law you had to memorize. It's just how reality works. Except it isn't. Not at the quantum scale. At the level of electrons and protons, particles don't just bounce off barriers. Sometimes they go through them. Not around, not over, through, without breaking the barrier. Without having enough energy to cross it, they simply appear on the other side. This is called quantum tunneling, and it isn't theoretical. It's happening right now, inside the sun. Nuclear fusion shouldn't be possible at solar core temperatures. The protons don't have enough energy to overcome electromagnetic repulsion, but they tunnel through the barrier anyway, which means the sun is only burning because reality has a glitch. Your DNA uses it too. Mutations happen partly because particles tunnel through molecular bonds they shouldn't be able to cross. The hard drives storing your data, they rely on tunneling to function. This isn't a fringe phenomenon. It's load-bearing infrastructure of the universe. And the deeper question isn't how it works. The deeper question is, why does a particle have a probability of being somewhere it has no right to be? What does that say about location? What does that say about barriers? What does that say about the rules we thought were absolute? A wall is apparently just a suggestion. Number 8, the twin paradox. 2 twins, same birthday, same DNA, same moment in time. One stays on Earth, one boards a rocket and travels at close to the speed of light. Years pass, the rocket returns, and the twins are no longer the same age. One has aged decades, the other barely at all. This is the twin paradox, and it's not science fiction. It's a direct consequence of special relativity, confirmed by atomic clocks on aircraft, by GPS satellites that have to correct for it daily, by particle accelerators where unstable particles last far longer than they should because they're moving fast enough to stretch their own time. Time dilation is real, which means time is not a constant. It's not a clock ticking the same for everyone. It's a personal experience, elastic, relative. And here's the part that quietly unsettles everything. There is no universal now. 2 observers moving at different speeds don't just disagree about how much time has passed. They disagree about the order of events. What happens first for you might happen second for someone else. There is no master timeline, no cosmic clock everyone shares, just a fabric of space-time that bends differently depending on how fast you move through it. You're not moving through time. Time is moving through you, at a rate determined by your velocity. And somewhere out there, a clock identical to yours is ticking at a completely different speed. Number 7, the quantum Zeno effect. There's an ancient paradox, Zeno of Elea, 450 BC. An arrow in flight. At any single instant, the arrow isn't moving. It occupies one position, just one. So when exactly does it move? He meant it philosophically. Physics turned it into something far stranger. Because it turns out, watching something can actually stop it from changing. Not metaphorically, literally. This is the quantum Zeno effect. Unstable quantum systems, particles on the edge of decay, will decay on a predictable timescale, unless you measure them, repeatedly, rapidly. If you observe an unstable particle frequently enough, it doesn't decay. The act of measurement resets its countdown. Watching it freezes it. This was predicted in 1977 by Misra and Sudarshan, then confirmed experimentally. In 1989, researchers held unstable ions in a stable state simply by watching them often enough. The measurement wasn't passive, it was intervention. Observation wasn't recording reality, it was shaping it. And that's the part you can't shake. If a particle's behavior changes because something is watching, what is watching exactly? A detector? A photon? A conscious observer? Physics doesn't specify. It just says the interaction matters, which means reality, at its most fundamental level, responds to attention. The universe behaves differently when no one is looking. That's not poetry. That's a peer-reviewed result. Number 6, the ultraviolet catastrophe. In the late 1800s, physics was nearly complete, or so they thought. The equations were elegant. The predictions were precise. Scientists genuinely believed they were close to a final theory of everything. Then, someone asked a simple question. How much energy does a hot object radiate? Should be easy. Plug in the numbers, get the answer. So they did. And the answer came back, infinite. Not large, not approximate, infinite. According to classical physics, a glowing piece of metal, a light bulb filament, a candle flame, anything warm, should be radiating infinite energy at ultraviolet frequencies. Every heated object in the universe should be releasing energy without limit. Reality should be catastrophically bright. And yet, a light bulb just lights up a room. The equations were describing a universe that clearly didn't exist. This became known as the ultraviolet catastrophe, and it didn't get patched quietly. It broke classical physics completely. Max Planck fixed it in 1900, but only by introducing something radical. Energy isn't continuous. It comes in discrete packets, quanta. He called it a mathematical trick at first. He didn't believe it was real. It was real. That desperate fix became the foundation of quantum mechanics, the most precisely tested theory in scientific history. An entire revolution in human understanding started because a light bulb refused to destroy the universe. The equations said it should. Reality said no. Reality won. Number 5. Wave-particle duality. Pick up a rock. It's a thing. It's in one place. It has a defined edge, a defined mass. It does not spread out across space like a ripple on water. It's a particle. Now fire an electron at a barrier with 2 narrow slits cut into it. You'd expect the electron to pass through one slit, land on the wall behind it, leave a single mark. That's what a particle does. But that's not what happens. The electron passes through both slits simultaneously. It interferes with itself, like a wave, and creates a striped pattern on the back wall that a single particle has no right to produce. It behaves like it spread out, explored both paths, and collapsed back into a point only when it landed. So you try to catch it. You place a detector at the slits to see which one it actually goes through. And the moment you do, the interference pattern disappears. It stops behaving like a wave. It picks a slit, acts like a particle, as if it knew you were watching. This is wave-particle duality, and it's not a flaw in the experiment. It's been confirmed thousands of times. The electron doesn't have a definite nature. It has a nature that depends on the situation. Observed, it's a particle. Unobserved, it's a wave. Both, neither. Something language doesn't have a word for. Because nothing in human experience behaves this way. Nothing except the fabric of reality itself. Number 4. The Ebar paradox. Einstein hated this one. Not because it was wrong, because it might be right. Here's the setup. 2 particles interact. They become entangled, their quantum states linked in a way that can't be separated. Then you pull them apart, across a room, across a city, across the universe. Doesn't matter. Now you measure one of them, instantly, not after a delay, not after a signal travels. Instantly, the other particle resolves into a corresponding state, as if it knew, as if information passed between them at speeds that make light look stationary. Einstein called it spooky action at a distance. He was being dismissive. He thought it proved quantum mechanics was incomplete, that there had to be hidden variables, local instructions each particle carried, that explained the correlation without requiring impossible communication. He was wrong. In 1964, physicist John Bell designed a mathematical test, a way to determine whether hidden variables could explain the results. Experiments ran. The results came back. No hidden variables. The particles aren't carrying secret instructions. The correlation is real. The connection is real. And it's instantaneous, which creates a problem physics hasn't cleanly solved, because nothing should travel faster than light. That's not a guideline. It's a foundational law. And yet, something connects those particles. Something that doesn't care about distance. Something that doesn't travel at all. Maybe space itself doesn't separate things the way we think it does. Maybe separation is the illusion. Number 3, the black hole information paradox. There is a law in physics that almost nothing violates. Not black holes, not explosions, not the death of stars. Information cannot be destroyed. Not the data itself, the physical information encoded in every particle, every arrangement of matter, every quantum state of every atom that has ever existed. Burn a book, the information survives. Scattered in smoke and ash, theoretically recoverable if you could track every particle. The universe keeps records, always. Then a black hole enters the picture. Matter falls in. Light falls in. Information falls in. And in 1974, Stephen Hawking showed that black holes slowly evaporate. They emit radiation, now called Hawking radiation, and over astronomical timescales, they shrink, and eventually vanish. But here's the catastrophe. Hawking radiation is thermal. It's random. It carries no information about what fell in. Which means when the black hole disappears, everything that ever crossed its event horizon is gone. Not scattered, not encoded somewhere. Gone. Destroyed. That violates the law, completely. Physicists have spent 50 years on this. Hawking himself changed his position. Some say information escapes encoded in subtle correlations. Some say it's preserved on the event horizon like a hologram. Some say the black hole leaves behind a remnant. Nobody agrees. Nobody has solved it. Which means there's a place in the universe where the rules break down completely. A drain in reality where information goes and doesn't come back. And we built our entire understanding of physics on the assumption that couldn't happen. Number 2, the measurement problem. Here is the most uncomfortable sentence in physics. Quantum systems don't seem to have definite properties until they're measured. Read that again. Not we don't know the properties until we measure. Not a gap in our knowledge. The properties don't exist in definite form until something interacts with the system. Before measurement, a particle has no single position, no single spin, no definite state. It exists as a superposition, a blur of all possible states simultaneously, described by a wave function that evolves smoothly and predictably. Then something measures it, and the wave function collapses. All possibilities, gone. One outcome. Definite. Real. Singular. This is the measurement problem. And the problem isn't the collapse itself. The problem is that quantum mechanics cannot tell you what causes it. The equations describe everything before measurement. The equations describe everything after. But the moment of collapse, the transition from possible to actual, is not in the equations. It's a gap, right at the center of the most successful theory in physics. And physicists have been filling that gap with interpretations, not solutions. The Copenhagen interpretation says, don't ask. Many worlds says the wave function never collapses. Every outcome happens in branching parallel universes. Objective collapse theories say something physical triggers it. Relational quantum mechanics says properties only exist relative to an observer. Decades of debate, no consensus. Because nobody can agree on what measurement actually is. Nobody can agree on what an observer actually is. Nobody can agree on what reality actually is between one moment of observation and the next. Which means the foundation of quantum mechanics, the most tested theory humanity has ever produced, contains a question it cannot answer. What is real when no one is looking? Number 1. The fine-tuning problem. Forget the paradoxes for a moment. Forget the particles and the black holes and the collapsing wave functions. Go deeper, below all of it, down to the numbers, the raw constants embedded in the laws of physics, g of light, the gravitational constant, the mass of an electron, the strength of the electromagnetic force, the cosmological constant, the energy density of empty space. These numbers weren't derived. G weren't calculated from something more fundamental. They simply are. Built into the universe at its origin. And here's what makes physicists go quiet. If any of them were even slightly different, not drastically, not by orders of magnitude, slightly, nothing would exist. Change the cosmological constant by 1 part in 10 to the power of 120, and the universe either collapses instantly or expands too fast for matter to ever form. Change the ratio of electromagnetic force to gravity, g a fraction, and stars never ignite. G no stars, no carbon, no chemistry, no life. The window for a universe like ours is extraordinarily narrow, absurdly narrow. The kind of narrow that, in any other context, would not be called coincidence. And nobody knows why the numbers are what they are. Some invoke a multiverse, infinite universes, each with different constants, and we simply find ourselves in one compatible with our existence. Some invoke design. Some say there's a deeper theory we haven't found that makes these values inevitable. None of these answers are satisfying. None of them are confirmed. Because the deeper you look, the more it seems like the universe was configured, precisely, deliberately, for something. The most unsettling part, the part that lingers, is that physics has no mechanism that produces fine-tuning. It just finds it, sitting there, waiting there, like a message written in the constants of nature that we don't yet know how to read. 10 paradoxes. 10 places where reality stops making sense, and maybe that's the point. Every time physics hits a wall, something new is waiting on the other side. Quantum mechanics, relativity, the universe, expanding into nothing we can name. We are the only species we know of that gets to ask these questions. That might be the strangest thing of all. Not that reality is glitched, but that something inside it noticed.